Okay, guys, so I tried again and I got this far before it cut off. So I'm just going to leave the words here and we'll talk through them. So we were saying we were giving a definition for an absolute or a global maximum. And what an absolute or global max is, it's a value x equals c that's higher than any other point on the function. So if you look at the graph that I've drawn down here, we can see that this point right here, the little pink point at the top there, is a global max because it's higher than anywhere else on the function. But there is no global minimum. So a global minimum is a value that is lower than any other points on the function. There is no global minimum here because there is no value that's lower. Because it's going down forever on both sides there, it's just going to keep getting smaller and smaller forever. So there will be no value that's lower than anywhere else. Okay, so global max, higher than everywhere, global min, lower than everywhere. So then in the second graph, we can see that that global min is that point that we have here, the pink point right there, that's just lower than everywhere else on the whole graph. And this graph has no global max because it keeps going forever right here. So it'll always keep getting higher. There's no place that's higher than everywhere else. So that said, if we go back and look at the first graph, we have this place right here that's lower than everywhere else around it, but it's not lower than everywhere else on the whole curve. So it's not a global minimum, but it is some sort of minimum. In the same way that this point right here is higher than everywhere else around it, so it's not a global maximum, but it is some sort of maximum. So this we call a relative or a local maximum, and a relative or a local minimum. So here we can say relative local extrema. And that is when a value x equals c is higher than not everywhere on the graph, but just everywhere around it. So a function f of x has a relative maximum, which we can also call local, and you'll hear me use those words interchangeably, at x equals c. If it is higher than everywhere else around it. Is higher than the values, we'll say close to it, on the right and left. And it has a local min in the same way if it's lower than those values. Has a relative or, local minimum at x equals c if it is lower than values close to it on the right and the left. So if we go back up to the graph, I can see that this is a local max. This is my local max. And this is my local min. So I'm going to draw a graph that has a whole bunch of local min, and we're really going to focus mostly on those right now. We'll think about global later. Okay, so we have this graph here. Let's say that it looks something like this. So I go up, and then I go down, and then maybe I have this happening, and that happening, and then that. Okay, so if I look at this right here, the first thing I want to point out is that these values right here are higher than anywhere else on the function, but they have the same value. So I consider them both to be global maximum. So in other words, a function can have more than one global maximum. So a function can have more than one global max or min if they occur at the same y value. So then the second thing is that even though these are global max, I can also consider them local max. So global is because they are still higher than everywhere else around it. So a local max is not always a global max, but a global max is always a local max. So in other words, it's a maximum, it's bigger than everywhere else. That means it's bigger than everywhere else around it. So this is also considered to be the local max. Now this right here is a local min because over here on the left side, it has it going down forever, which means it's not the lowest point on the function, it's just lower than everywhere around it. And right here, I have a max and a min. So that's my local max, and that's my local min. And if we're paying attention, I can see that these local max occur at those horizontal tangent lines, or what's happening right there? That is a corner, so the derivative does not exist. So that's at places where the derivative equals to 0 or where the derivative does not exist. So in other words, local max and min occur at critical values. Those critical values were the places where the derivative does not exist or where it equals to 0. And this is what's called Fermat's theorem, actually. Fermat's theorem says that if there is a local max or a local min at x equals c, then that x equals c is a critical value. So we're going to write Fermat's theorem in the simplest way possible. Fermat's theorem tells me that local extrema occur only at critical values, meaning that they're not going to occur anywhere else. So when f prime of x is equal to 0 or f prime of x does not exist. Now the second thing, though, that's important, that's not really part of Fermat's theorem, but it says local extrema only occur only at critical values, so when f prime of x equals 0 or f prime of x does not exist. But this does not mean that every critical value is a local extrema. And in fact, the values that we're seeing could be things like asymptotes or discontinuities where there will not be an extrema there. So we'll say, but not all critical values will be local extrema. Okay, so with that said, this brings us to what's called the first derivative test. The first derivative test. And what the first derivative test tells me is how I can use that variation table that we made up there to where we said, hey, it's increasing here and decreasing here to determine where I have local max and min. So the first derivative test tells me, first off, if I look at this max that I have right here, notice on the left side it's increasing and then it's decreasing, increasing and decreasing, increasing and decreasing. So it says if the function changes from increasing to decreasing at a critical value, then I have a maximum. So if f prime changes from plus to minus, so from increasing to decreasing at x equals c, and f of c exists, then f of x has a local maximum at x equals c. And then the second thing says, well, if I look at where these minimums occur, notice I'm decreasing and then increasing. I'm decreasing and then increasing. So if I go from decreasing to increasing, I'm going to have a minimum. B, if f prime changes from -2 plus, so in other words, that's f changing from decreasing to increasing at x equals c, and f of c exists, then f of x has a local min at x equals c. And then the last thing this says is that if it doesn't change signs at that critical value, then there is no max or min. Does not change signs at x equals c, then f has no local max or min. Okay, so this is the first derivative test. Now I'm going to actually go back up here and add a thing, and that is if x equals c is a critical value. So that follows from Fermat's theorem, but it also sort of helps us to think about how I can apply this test. So I'm going to go back to the first problem that we did here, where we have our variation table. And what I'm going to do is check if f of x exists at each of the critical values. So I'm actually just going to recopy all of this stuff down because I think that's the safest way to do this so that we're not writing on top of stuff. So we had f of x is x to the fourth plus 1 over something. I forgot. Over, it's gone. Over x squared. So previous example, we had f of x is equal to x to the fourth plus 1 over x squared. F prime of x was equal to 2 times x to the fourth minus 1 over x cubed. And then our variation table, we had our intervals from negative infinity to negative 1, negative 1 to 0, 0 to 1, and 1 to infinity. Then my test values, I'm just going to do the same thing. So we have exactly the same variation table, 1/2 and then 2. And then we had what was going on with f prime and what was going on with f. So f prime, we had negative, positive, negative, positive, so that it was decreasing, increasing, decreasing, increasing. So to apply the first derivative test, check that the critical values are, f of x is defined at the critical values. Test, check that f of x is defined at the critical values. And here I can see that the only problem f of x has is 0, because that's the only thing that will cause division by 0. By 0, that's when x squared equals 0, so x is equal to 0. So this critical value right here, f of x is not defined. So I can write f of x does not exist. And actually even, if I'm doing like f of 0, then I get 0 plus 1 over 0. That's a vertical asymptote. That's a constant over 0. That's a vertical asymptote. So it actually makes more sense to write a vertical asymptote right there. So what that means is I'm not going to have a max or a min there. I have a vertical asymptote instead. Now, here I go from decreasing to increasing at -1. So that makes this a local min. And if I draw decreasing then increasing, I can kind of see that local min. And again, this goes from decreasing to increasing. So I also have a local min right here, decreasing, increasing. So in other words, there is a local min at x equals -1 and x equals 1, and there is no maximum. That said, when we are asked to find the local extrema, so if I were to say, example, find the local extrema of f of x equals x to the fourth plus 1, the local extrema of f of x is equal to x to the fourth plus 1 over x squared, then I always want to make sure that I find the y value as well. Need to find y value as well. So here we can use our variation table to conclude that there is a local min at x is equal to -1 at the critical value. F of -1 is equal to -1 to the fourth plus 1 over -1 squared is equal to 2. And at x is equal to 1, which is f of 1, which is also 1 plus 1 over 1, which is also 2. So 2 local min at -1, 2, and at 1, 2, and no local max would be my final answer here. Okay, so we're gonna finish with one problem where we find a variation table and the local extrema just all in one go. All right, so my example here will be, let f of x equal to 4x plus 1 over x. So find the intervals of increase and decrease and all local extrema of f of x is equal to 4x plus 1 over x. So we're going to follow our guidelines from before. Our step 1 was to take the derivative. So my step 1, I take the derivative. So I'm like, f prime of x is equal to 4 minus 1 over x squared. So that 1 over x, remember, is like x to the -1. Okay, then we want to find the critical values. So here we're looking for the critical values. And so I have two things going on. F prime is equal to 0. And in this case, because this isn't just a fraction, I actually have to set the whole thing equal to 0. So I have 4 minus 1 over x squared is equal to 0. So that gives me 4 is equal to 1 over x squared. I move that to the other side. So I'm going to add plus 1 over x squared plus 1 over x squared. Then I'm going to multiply both sides by x squared to get 4x squared is equal to 1. Then I'll divide by 4 to get x squared is equal to 1/4. When we do the square root, we need to remember plus or minus. So x is equal to plus or minus the square root of 1/4, which is 1/2. Then f prime does not exist. That's going to be when we have division by 0, which will occur when x squared is equal to 0, which is when x equals 0. Now, because I'm also asked to find the extrema here, it makes sense to check whether or not f is defined at these. That said, with f prime equals 0, that's a horizontal tangent line. So of course f is defined. With x equals 0, though, the derivative does not exist. Those are the only values I actually need to check. Only need to check if f of x exists at critical values when f prime does not exist. So f of 0 would be 0 plus 1 over 0. That gives me that constant divided by 0, so it is not defined. And in fact, I get a constant over 0, so I have a vertical asymptote here. Okay, so this brings us to our third step, which is to set up our variation table. We got 3 critical values here, which were x is equal to -1/2, 0, and 1/2. So those are the values that I'm using in my variation table. So I write I for interval, and then I have -∞ to -1/2, -1/2 to 0, 0 to 1/2, and 1/2 to infinity. There we go. Okay, so then I want to pick a test value on each of those intervals. So I'm going to pick -1. So that's like -0.5 to 0. So I'm going to pick like -0.25 or -1/4. If you want to use decimals here, that's sometimes helpful. And then I'm going to pick 1 over here. And then I'm plugging those values in to f prime and to get a sign. So here I'm looking for f prime of -1, which is 4 minus 1 over -1 squared, which is positive. So I'm going to put a plus sign here. And then I'm going to have a minus and a minus and a plus when I plug in each of the other things. So f prime of -1/4 is equal to 4 minus 1 over -1/4 squared, which gives me a negative value. F prime of 1/4 will give me the same thing, exactly the same thing. And f prime of 1 will give me the same thing as well. So as when I plug in -1, so I'm going to get back to a positive value here. I just wrote positive there, I meant negative. Okay, so those are our signs. So then we make our conclusion about f. And so we have increasing, decreasing, decreasing, increasing. And the very first thing that I'm going to do is write vertical asymptote at 0, because I don't want to accidentally make the conclusion that that's a max or a min. It's a vertical asymptote, it is neither. But here, this is going up and then down, so that's a local max. And this is going down and then up, so that's a local min. So then my final answer to this question is f of x is increasing on -∞ to -1/2 union 1/2 to infinity. And f of x is decreasing on -1/2, 0, union 0, 1/2. So that's my final answer about increasing and decreasing. Then we want to find the y values of our local extrema. So I have a local max, a local max at x is equal to -1/2. So I plug that in to my original function, f of -1/2. My original function was 4x plus 1 over x. So that's 4 times -1/2 plus 1 over -1/2, which gives me -2 minus 2, which is -4. So my local max is -1/2, -4. And then this does have a local min. So I have a local min at x is equal to +1/2. So f of 1/2 is 4 times 1/2 plus 1 over 1/2. So that's 2 plus 2, which is equal to 4. So my local min is at +1/2, 4. And I don't have to worry about 0 at all because that was my vertical asymptote. So that's my final answer to this question, and we can see how we can use this variation table to find intervals of increase and decrease and also local extrema. That's all for today. Bye, guys.